Okay, Assalamualaikum. Selamat Hari Raya. So this is our first class after Hari Raya break. Okay. So in the previous video, we have learned about subchapter 2.1, already covered in the last video about the cooling curve and so on lah, and how to develop phase diagram. Okay, so for this class, for this session, we are going to learn about the phase diagram itself. It is more detailed about the phase diagram. Okay, so at the end of this subchapter, the objective that that you should have to obtain about the to discuss the various phase region for simple binary phase diagram, to determine the phase present, composition, and relative amount of phases. And also you have to discuss the development of the microstructures upon cooling for several situations, and to locate the invariant point and right reaction for all the transformation for either heating or cooling. Okay, sounds complicated, but don't worry, we are going to understand along this video. Okay, so let's go to the first slide about the first diagram. Normally we have to know the basics. Okay, what is the phase diagram? Okay, by definition itself, it is a graphical representation here. Okay, what it represents the phases in a material system at various temperature, pressure, and composition. So we have three variables, three factors here that are presented in the phase diagram. You will have the temperature unit, pressure value, and the composition percentage in the phase diagram. So why do we need to know about the phase diagram? Okay, it is because there is a strong correlation between microstructure and mechanical properties. Okay, besides, development of alloy microstructure is related to the characteristics of its phase diagram. So why it is very important in the applications? Because by knowing the phase diagram, it is important during the casting process and also the soldering process. Okay, so this is the example of the phase diagram for pure water. Okay, we know that the water can be found in the liquid and also as a steam or vapor, and also as a solid, but we call it ice for the water, right? Okay, like I mentioned earlier, we have the value of temperature, pressure, and composition itself of the water in the phase diagram here. Okay, wait a second. Okay, so you can see here, this is the point where it meets three lines here. This is what we call the triple point, because at that point we have three phases found in that condition. Okay, one is the solid here, so here is the solid, and around here is the liquid phases, and the below is the vapor steam. So it meets all together at this point, the point that we call the triple points. Okay, you can see the video in the YouTube here about the triple point of water, what it is all about. Okay, this video doesn't have any sounds or music, so you have to focus on the video itself. Okay, around here we have liquid, water liquid, and here is the ice. But you can see here there are bubbles. Bubbles mean that it contains the gas or vapor of water. The vapor of water, we call it steam, right? Okay, so now we have three phases found in these conditions. Okay, you see here at this point in time the water is starting to boil. So it boils, it will convert it into the vapor phase. Okay, so this is the solid, this is the liquid, and the bubble represent for the vapor. Okay, so quite fascinating, right? So that's what we call the triple points. Okay, I think you also learn about the phase diagram in the thermodynamics, but maybe not as detailed in the phase diagram of the material science. Oh, sorry. You are going to learn the thermodynamics in the semester 4. So you now currently in the semester 2. So never mind, you are going to meet another phase diagram in the thermodynamics when you study the thermodynamics in the semester 4. Okay, 4th semester. Okay, so let's go to the next slide. Okay, phase diagram. There are three types of phase diagram. Okay, there are three terms you have to remember: unary, binary, and ternary. So U is for the single, bi is for the two, and tertiary for the three. So what it means here in the phase diagram is that when you have the binary, means that it consists of two components in an alloy. As we know, alloy is the combination of two or more elements. Okay, so here two or more metal elements, there is alloy. So here when we know that there is the binary phase diagram, so automatically you have to know that there are two components in that phase diagram. Okay, if it is unary, so only one component. So basically for our syllabus here, you are commonly will have the binary phase diagram. Okay, so this is the example of unary phase diagram. This diagram of the water also is the unary because it only contain pure water. Okay, so this is the ternary phase diagram. You have the Cr, you have the ferrum and nickel. Okay, so there are three elements here: chromium, ferrum or iron, and also nickel. So it will look like this for the ternary phase diagram. And for the syllabus, as I mentioned, we are focusing more on the binary phase diagram. So by the definitions, the binary phase diagram consists of two components in an alloy. So the types have complete solid solutions. Copper and nickel are completely soluble, and no solid solutions. Okay, plumbum insoluble in copper, limited solid solution. Strontium has limited solubility in plumbum, or sometimes we call plumbum here is lead. Okay, so this is about the argentum and aurum. Okay, here it states that it is liquid phase along here in the green region, and below that we have the orange here is the alpha phase. Okay, alpha, sometimes we use alpha, symbol alpha, that's mean for the solid. So how about the region in the pattern of line, horizontal line here in the blue line? Okay, this is like the intermediate phase between the liquid and the alpha phase here, solid. So if we have a particular point here, so it means that we have liquid and solid. Okay, so that's the beauty of the binary phase diagram, because you can determine the phase conditions at what temperature on that particular percentage of compositions. Okay, so let's go to the next slide. Okay, binary phase diagram. Here there are three types of binary phase diagram as stated here. Okay, so we have the complete solid solutions. Okay, what it means? It means that complete solubility in liquid and solid, okay, results in single phase. Yes, that's why we have the name complete solid solutions, because it only resulting in single phase. Okay, as example of copper and nickel. Okay, and the second type is the no solid solutions. Here, no solid solutions. Okay, oil and water results in multi-phase. Okay, other example of the platinum and copper. Okay, why? Because it cannot mix between two elements here. As example, oil and water cannot be mixed, so it completely separated. So that's why we call it no solid solutions. Okay, and the third one is the limited solid solution. Okay, so as example of the salts and water, we try to mix the salts and water. When you pour the salts into the water, and some of the salts remains at the bottom of this cup, means that they are the excess salts, so it cannot mix 100%, so it is not completely soluble. Okay, so at certain point it only has the limited solid solution, only limited solubility. Okay, so it also results in multi-phase. Okay, example of the alloy is the composition of zinc and copper, and strontium and platinum or lead. Okay, I hope you still focus on this video. If it is quite boring, you can pause, have your own little break, 2 or 3 minutes, and then come again. Okay, and then study again this video, because it is very I know it's very boring. This is all about the material science. Okay, but nak tak nak kena jugalah. Okay, so the name of the complete solid solution for the phase diagram, we call it isomorphous. Okay, binary isomorphous phase diagram. So isomorphous, let's go back to the complete solid solutions. Okay, so it means that it is complete liquid and solid solubility. Only one solid phase form, same crystal structure. Only one solid phase form. Okay, here only one. The key point here, one solid phase form. So here only FCC solid solutions. Okay, So the isomorphous phase diagram, okay, that their name lah, hanya nama lah, isomorphous phase diagram. So we have the liquid here and only one solid solution below here, down below here. So we have the intermediate region here. It represented by the letter L. L represented for the liquid, and alpha is for the FCC solid solutions. Okay, so as example here for the copper and nickel system, two phases found in this phase diagram. Yes, we know it has the liquid L and the solid alpha. Okay, three different phase fill region. One is the liquid phase here, 100% liquid, yes, completely liquid. And then the second phase is what we call the two phases, the intermediate phases here, two phases where it is found in the liquid and also in the solid. Okay, and finally alpha phase, where it only found in the solid. Okay, so substitutional solid solution consists both copper and nickel. Okay, note that liquidus is line above here. Line here, we name it liquidus, is line above which all of alloy is liquid. So this is the border. Ni lah limit untuk liquid cair. And then solidus here is the line below here. Okay, ni limit border dia, sempadan antara two phases and the solid. Okay, jadi kita namakan dia solidus, liquidus and solidus. Okay, binary isomorphous phase diagram and types of phase. Okay, rule 1, if we know the temperature and the composition, then we know what types of phase present at that point, at that condition. Okay, as example, kalau dia cakap, okay, satu point A at 1100 Celsius and at that 60% of composition. Okay, so kita simple je, simple mencari dalam graph. Kita carilah point 1100, 1100 temperature here. Okay, and then second value is 60% composition, so that is the point of A. Yes, and then where is the point of A? In this phase diagram, we know that it is in the alpha region, alpha phase. So it is only one phase of alpha. Okay, second example is the point B, where the temperature is 1250, around this one. Yeah, right? And then 35% percentage. Around this one is 30. Okay, this is around 35. And then the point is in the region of two phase, right? We have liquid, we have solid, we have L and alpha. So you just put it L plus alpha. Okay, so simple, right? Senang je, jangan risau. Cuma kena ingat perkataan-perkataan sajalah. Okay, so this is extra information. Some common features of phase diagram, alpha, beta, and gamma, and etc., are used to indicate solid solution phases, and L represent a liquid. So maybe we use the beta here for the solid, and also we can use the gamma symbol. So when you see the alpha, beta, and gamma, straight away you know that there is the solid phase, solid solution. Okay, so rule number 2, if we know temperature and composition, then we know the composition of each phase, weight percent and weight percent. As example here, at the copper of 35% of nickel, so around this here, copper 35 composition, nickel, copper and nickel. And then if the temperature at TA, Cl equal to Co at that point, so if we have the temperature TA and then we find it here, it is the liquid, only found liquid, right? And for the TD, at TD around here, still at that composition 35%, so we know that it is solid. And for the TB here, the temperature here, we projected to the 35% composition, and then now we know both alpha and liquid. Okay, but we know the limit percentage of composition. If we put it 32%, so it must be in the liquid phase. And for the C alpha here, the limit here is around 43%. So determination of phase composition, this is the rule here. You have to know, first one is to locate the temperature, and the second one, the second step, if one phase present, the composition equal to the overall composition of alloy. And the third step, if two phase present, use tie line. This one is the tie line. Okay, so this is how you write the answer if it is found in the two phase region here. So you have to write down the Cl, the composition for the liquid, the limit here in the for the liquid phase, and also composition of the alpha, the solid here. So you have to write down 32% and 43%. Okay, for the solid, for the pure solid solution and the pure liquid, you just state down like this: only liquid, blah blah, only liquid, only solid, blah blah. Okay, so rule number 3 for the weight fraction of phase. If we know temperature and composition, then we know the amount of each phase. Okay, single phase 1 or 100%. Okay, single phase, yes, of course it is 100% pure single phase. That if in the liquid, 100% liquid. If in the alpha, solid, so there is 100% solid. Okay, so example of composition 35%, at the TD, so we put it 100% liquid with weight percent there. Okay, weight fraction there. So tulis WL 100% and W a liquid at A, yeah, right here. So WL here 100%, but W alpha, no, there is no alpha here because this is 100% liquid, so you put it 0. And for the TD, at TD here, you project that point D is in the region of the alpha, and then so we write down the weight percent of liquid is 0, but for the weight of solid alpha equal to 100%, WT percent. Okay, why you have to put WT percent? This is the symbol of weight fraction. Okay, must write down WT And how about the TB? Okay, so this is a tricky one. When you found the point is in the region of the liquid and the alpha here, so you have to do a simple calculations. The limit here, or we call it C alpha, is 43, right? And the Cl liquid is 32. So you have to do the ratio percentage here. Okay, 43 minus 35 over 43 minus 32. So here 43 is C alpha, 35 is our C. Yeah, and then this is C alpha minus the limit of Cl. So you have to times 100% lah to get the percentage, or we just write down in the fraction form where 1 equal to 100%. So 73% equal to 0.73. Okay, so this is the WL. Yep, for the liquid. And for the W alpha, you have to reverse, or in the easy way, 100 minus 73, so that you get 27%, or 0.27 in the fraction form. Okay, so note, within single phase alloy, the alloy is completely 100% Z phase. Okay, if two phase alloy exists, use lever rule. Lever rule is what I said about the fraction calculation here. Okay, limit minus the our value over limit, upper limit minus the lower limit. Okay, that is the lever rule. Lever rule here. Okay, so this is the example of the rule 1, rule 2, and rule 3, the isomorphous phase diagram. So this is the lever rule. You can see some kind of the explanation how to calculate. Basically, it is just the mathematical calculations. I think you already know in your mathematics SPM, okay, sometimes ago. Okay, the other example, consider an alloy containing 50% percentage of nickel and 50% percentage of copper at 1300 Celsius. Calculate the relative amount of each phase. Okay, so this is 1300, 50%, so this is the 50%, around like this. Okay, so you have to use the ruler. I try to use the line here. Oh, you have problem with Microsoft Notes, so you cannot do that particular points. Oh. Still cannot. Okay. I just estimate draw here. Okay, so this is my point, and then you have to use the tie line. So this is the CL, and this is the C alpha, and then we project here. We have the value of C alpha, approximately 60%, and here is CL around 45. Okay, that is my approximation. Okay, but the value here is given. where the CL accurately at 44 and for the C alpha is 57. So yes, you have to use your ruler. Okay, and then the CO is 50%, of course. The CO is 50%, our C composition. Okay, so for that WL, you can calculate as I have shown before. So 57, so cancel that 60, 57, and then CL is 44. Okay, 57 minus our CO is 50, and the C alpha here, C alpha 57, okay, 57 minus our CL here is 44. Yep, so the value is 0.54. So if you want to calculate for the weightage weight of the alpha, yes, you can calculate using this calculation. It's just the reverse order of the WL, but if to save a little bit your time, just 1 minus 0.54, and then you will get 0.46. That's it. Okay, simple, right? So this is your exercise in your manual, in your notes. Okay, the results or the answers is here. Okay, you can do by your own, and then double check your results with these answers. Okay, I give you 5 minutes break. Okay, and then you resume this video for the next slide. Okay, make sure you do this exercise. Okay, so we have 5 minutes break. Okay, let's continue with our learning session. Okay, so I hope you get the right answer for this exercise. And now we go to the microstructure. Okay, from the phase diagram, okay, that we have learned how to determine the phase present at that particular point, where you know the value of temperature and the composition. Okay, and then the information we obtain here is the information of the process conversion. Okay, as example here, as the point A here is the liquid, so it 100% liquid. So the microstructure is only green, that represented by the green color circle here. Okay, so this means that the green is liquid form. And then when we go a little bit lower in the temperature, so you cool a little bit, and then where it reach the liquidus line, okay, and just a bit lower than liquidus line, so you are in the liquid and alpha phase region here. So the blue dot start to exist, so it means that the solid start to initiate. So we call it initiation of solidification. Solidification, proses pembekuan lah lebih kurang. Okay, menjadi solid, berpejal. Okay, so ni baru initiation, start, baru bermula. So first solid will form, or first liquid to solidify. Itu maksud dia. Okay, sekejap saya nak double check betul record. Okay, kan tak record suara. Okay, so a little bit cooler, more cooler than B, around C, saya tak tahu lah berapa temperature, tapi lagi rendah. So dia akan bertambahlah solid dia. So that one is 27.3%. And then the liquid still majority here, still dominant. Dia found in the 72.7%. Macam mana dapat accurate value ni? Yes, by the level rule that you calculate as in this example. Okay, so we know that dekat C start banyak dah liquid solid. Okay, we go down to the D, just above the solidus line. Okay, so sini dah hampir 100% solid, tapi masih lagi ada liquid. So dekat around D, little liquid left, hanya sikit je tinggal. Okay, so last liquid to solidify, hampir-hampir dah nak habis. So diagram dia bentuk macam ni lah, structure dia. Yang biru ni solid, yang hijau ni liquid, macam saya cerita tadi kan. Okay, so finally it completely in the alpha region, alpha solid phase. Okay, so that one we have no more liquid left. Okay, so 100% in the crystal structure here. Yang crystal structure ni adalah solid. So this one is the 100% solid. Okay, itulah. So example macam ni kita tengok. Okay, kalau awak kena lukis diagram microstructure macam ni, dia cakap draw and label the microstructure changes during a slow cooling process at temperature. Dia cakap dekat mana? Dekat 50%. So awak cari 50% ni, buat straight line naik atas 50%, and then start at the temperature T1 1400 kat sini. Okay, ni T1, lepas tu T2 sini kan, lebih kurang T2, and then 3 1200 kat sini, and then T4 1100 kat sini. Okay, so T1 kita tahu 100 solid, so buat je lah macam ni, buat kosong je, tak payah color lah kan, sebab tadi ada color. So untuk awak tak payah color lah, awak hanya tulis 100% liquid. So saya pemeriksa ke orang lain pemeriksa ke faham lah 100% liquid. Okay, so bila dia dah masuk solid plus liquid region dekat sini, so kita tahu dekat sini masih lagi banyak liquid. So awak tulis dekat, tunjuk lah macam dia tunjuk ni, liquid masih banyak, cuma solid dah wujud alpha. Okay, alpha. Okay, sampailah dekat T3, we know that there is no more liquid phase. Okay, so ni 100%, that one is 100% solid. So awak buatlah bentuk macam structure macam ni. This macam kenapa structure bentuk macam ni? Sebab dia adalah polycrystal. Polycrystal structure yang kita dah belajar dekat chapter 1. Okay, turun ke T4 sama juga. Kenapa sama? Sebab dia dah tak berubah dah. Walaupun dia sejuk sampai 1000 pun, structure dia masih lagi sama because they are in the same region of solid. Okay, macam itulah cara nak lukis microstructure. Okay, for the cooling curve, okay, this is the example. For an alloy containing 50% nickel and 50% copper, okay, kena lukis lagi 50%. Okay, sketch the cooling curve for the alloy. Okay, cooling curve ni kita dah belajar dekat sebelum ni, chapter 2.1. Awak kena apply dekat chapter 2.2. Macam mana kita nak buat cooling curve ni? Ni. Tengok balik. Saya dah cerita dekat video sebelum ni. Belajar balik. Okay. Macam mana kita buat ni? Okay, daripada phase diagram, macam mana nak buat cooling curve? Awak tengok balik. So, that information we are going to apply here in this example. Okay. So, dia akan bentuk jadi macam ni lah. Kalau contoh 50%, okay, bermula mana, temperature mana. So, daripada tulis sini, kat sini dia akan turun suhu. Konsisten macam ni bentuk dia. Sampailah ke TL. TL ni temperature yang kena kepada liquidus line. Point dekat sini. So, kalau kena tulis suhu kat sini, TL ni around 1320 kot. Lebih kurang macam tu lah. Yang untuk ni dia akan dalam keadaan region liquid, dalam keadaan two phase region, two phases here, liquid and solid dalam sini. Sampailah dia dapat kat suhu sini, solidus line. Okay, around berapa? Sini saya estimate lah 1000, because that one is 1350. Di tengah-tengah kan. So ni lebih kurang 330 kot. Okay. Okay, yang ni 1100. Ni around 1100. Silap. Ni 250. Ni lebih kurang 1270 mungkin. Okay, 1270 mungkin lah. So jadi sini boleh tulis lah 1330. This one is 1270. Macam tu lah. Dah dapat kan cooling curve. Okay, so tadi adalah isomorphous phase diagram where we have the complete solid solution, and now we have the second type. We call it eutectic phase diagram, no solid solution. Okay, so saya rasa kita buat video lain sebab ni dah panjang dah, takut pening. So we are going to end this video only at this slide. So for next slide and for eutectic phase diagram, we are going to learn in the next video. So I will put it part 1, part 2 and part 3 and so on lah. So we are gonna have a multiple parts for this subchapter 2.2 phase diagram sebab dia panjang. Okay, so that's all for this video. So you have to continue with the next video. So let's have a break. Assalamualaikum and good evening. Okay, bye.